Okay, this is a quick review on the periodic table, its parts and trends. Okay, the periodic table is set up to function as a grid, but instead of using XY, we're going to use the terminology period and group. Now, there's a reason why we do that, and I'll explain in the next slide. First off, what we need to understand is that the periods are the long direction, so they are going to run in this direction. So that's period. And so let's number them. There's period 1, period 2, period 3, period 4, period 5, period 6, and period 7. Now the last two rows down here, the F block, they are in period 6 and period 7. They fit right here in this little slot. If they were to put all of these elements in this slot, they would extend the periodic table too long to fit on an average piece of paper. So what they've done, and be able to read it. So what they've done is they've taken the F block out and they've put them in their separate two rows down there, the lanthanides and the actinides. So now let's go back to the period. The period is the row, and now the groups. The groups are going to run the columns. So let's group 1, group 2, group 3, and etc. Up here to group 12. Then we have group 13, and I'll just put it on here, group 15, and the last group is group 18. So if you count the number of columns, 1, 2, 3, 4, those are the groups. So the groups will come into the columns. So now when we look for an element, what we're going to say is, let's say we want to find the element of nickel and what period and group it's in. So there's my element of nickel. And I'm going to look here, and I'm going to say that it's in period 4. So I'm going to write period 4. And then what I'm going to say is, well, what group is it in? So here's group 3, 4, 5, 6, 7, 8, 9, 10. It's in group 10. So I would write group 10. Now let's say for sulfur, very same, right? What period is it in? You can see right here that it's in the 3rd period. Remember, these, even though there's a disjoint here, anything in this row is in the same period. So this is in period 3. And then what group is it in? Well, it's under 16, so that means it's in group 16. And so there you have it. That's how you navigate the periodic table. Period, group. Okay, so why do we have periods and groups? What do they mean? Well, the period tells you the valence electron level. Which energy level has your valence electrons? So if an element is located in period 4, the valence electrons are in energy level 4. It also tells you the highest energy level that has electrons in them. So that's the same thing as the valence electrons. So if it's in period 4, that means that the highest energy of the electrons is energy level 4. It also tells you how many rings to draw in a Bohr model. So if you were to draw a Bohr model of the atom, you just look what period it's in, and that tells you how many energy level rings you need. So it's quite handy to understand what period is, because it tells you a bunch of things. Now the groups tell us how many valence electrons are in the atom. Each element in that group has the same number of valence electrons. Now there's a little catch here. The transition metals, which are these metals right here, which also includes these, can have variable valence electron numbers. And there's a reason for that. We're not going to get into that right now. But so for the groups, we're just going to label them. Group 1 has 1 valence electron. Group 2, 2. Now group 13, it doesn't have 13 valence electrons, it has 3. It's always the last digit. Group 14, and then 15, 16, 17, and 18. There's a maximum of 8 valence electrons. But every element in that group has that same number of valence electrons, except for, we'll get to that in a second, except for helium. Helium is the oddball. So let's circle helium real quick here. Helium is the oddball. Helium only has 2 valence electrons. So helium has 2 valence electrons. That's the only one that has 2 in that group. So 2 for helium. Right? But everybody else in that group, neon, argon, krypton, xenon, radon, all have 8. Right? Everybody in this group has 7. Everybody in this group has 6, 5, etc., etc. Right? All the elements in the same group will have the same similar Bohr models and Lewis dot diagrams. Okay? Remember, the transition elements, these elements in here, and the rare earth elements, these elements down here, don't have the same valence electrons all the time. And there's a reason for that, but we don't care about that right now. So group 1, 1, group 2, and then the rest. Okay, so let's talk about the parts or the families of the periodic table. Now, these families have specific names, and they mean that they all have very similar properties compared to each other as far as bonding, chemical properties, and things like that. So the first thing we're going to do is, before we even start that, is we're going to show you the staircase. So let's draw the staircase now. Okay, I've drawn in the staircase. The staircase separates the metals elements from the non-metal elements. So my metal elements are located to the left of the staircase. These are all my metals, and my non-metals are all to the right of the staircase. So metals again, non-metals. The next set of elements that we are going to talk about are the alkali metals. And the alkali metals are located in group 1 except for hydrogen. So we're just going to use a little squiggly here to indicate the alkali metals. So those are my alkali metals. The next group we're going to talk about are my alkaline earth metals. And so we're going to indicate that with purple. And those are all group 2. So those are those metals. The alkali metals and the alkali earth metals are very reactive. Now, the one thing that we have to recognize is in the alkali metals, hydrogen is not one of the alkali metals. Hydrogen is not a metal. It is a nonmetal. It's kind of out of place as far as the metals, nonmetals, respect to the staircase, but it's placed in group 1 because it has 1 valence electron, and that's the reason why. The next one we're going to talk about are the noble inert gases, and they are in group 18, and they are all these elements right here. All right. And they have full valence shells, so they are very unreactive. When an atom gets a full valence shell, it generally does not want to react with anything. So those are my noble inert gases. The halogens, salt formers, are group 17, and those are all these elements right here. Right, so those are the halogens, right, and then these were the noble gases. Okay, and we have the transition metals. We already talked a little about those. Those would be all these materials in here. Right. So those are my transition metals, groups 3 through 12. And the last one, or the second to last one that we're talking about, are the rare earth metals, or called the actinide lanthanide series, and those are all these in here, the bottom 2 rows. Okay. Those are those elements. That's also called the F block sometimes. And finally, the metalloids, semimetals. Now, they're not a group. They consist of a bunch of elements, but let's see what they are. Boron is one of those. Silicon is one of those. Germanium, arsenic, antimony, tellurium. And some people say that polonium is. For our class, we're going to say polonium is. So those are the metalloids. The metalloids have properties that are similar sometimes to metals, and sometimes they're similar to nonmetals because they're right along that staircase. Remember, that staircase is the boundary between the metals and nonmetals. So, for example, germanium is more metallic-like than arsenic, but it's not as much metallic as gallium or zinc. Arsenic is more metallic-like than selenium, but less metallic-like than germanium. Same thing with silicon. Silicon is much less metallic-like than aluminum, but much more metallic-like than phosphorus. So these elements are called the metalloids. Sometimes they have properties like metals, and sometimes they have properties like nonmetals. So here's a recap of all the things I just talked about. Most of the elements are metals. They're left of the staircase. Most are nonmetal. Most nonmetal elements are gases. They are unique elements on the periodic table. Hydrogen in group 1, but is not a metal. Mercury and bromine are liquid at room temperature. Helium in group 18 should have 8 valence electrons because it's in group 18, but it only has 2. All alkali metals are very reactive, generally not found in nature pure, and all elements after polonium, Po, are radioactive. They really have no stable isotopes. Okay, when we talk about periodic trends, we're talking about making predictions about properties of elements based on where they are on the periodic table, and that's it. Now, I'm going to talk about what we mean by trends, about what direction. So when we talked about the periods and groups, from now on when we say the trend across a period, we're going to we mean in this direction. So left to right when we talk about a period. And then when we talk about going down a group, we're starting from the top of the group and going to the bottom. So that's down a group. So down a group. So we go from left to right when we talk about a period, the trend, and then down a group when we talk about going down a group. So when I say the trend across a period, we always start at the left and go to the right. When I said down a group, we always start at the top and go down to the bottom of that group. Now, the first thing we have to understand is what we mean by force of attraction on the valence electrons in the nucleus. Remember, the nucleus is positively charged and the electrons are negatively charged. So there's a force of attraction between the two. And as that force of attraction gets stronger, those electrons are held in or held on tighter. As that force of attraction is weaker, those electrons are held less tightly or loose, right? And then, so the force of attraction, let's write it out here, the force of attraction is proportional to 1 over r squared, where r is equal to the distance between the valence electrons, or any electron, and the nucleus, okay? So when we talk about the force of attraction increasing, either we're adding more force of attraction by either adding more protons and electrons, or we're decreasing the distance between the two. Okay, so the force of attraction either goes up by increasing the forces that are doing the pulling, or decreasing the distance. Okay, so as we go across a group, so let's look across a group again. So across a group, the force of attraction is increasing. And we'll explain why when we get to all the other trends. And then as we go down a group, the force of attraction is decreasing. So the things you want to remember is the following. And the expression is high, right, tight. And then the other expression is on the bottom, low, left, loose. So when you're in the high right section of the periodic table, the electrons are held on tightly. When you're in the lower left-hand part of the periodic table, the valence electrons are held on loosely. Okay? So those are the two areas that we're going to be concerned with when we talk about trends. And that'll all start to come together once we start talking about the trends. Our first trend across a period is the atomic radius. And the atomic radius decreases. So that's what I'm showing here, the decreasing atomic radius. It goes from larger to smaller. Okay? So the atomic radius is decreasing. Now why is that? Well, the force of attraction, as we remember, is increasing. So the force of attraction increasing, which means that the electrons in the valence shell, are pulled in tighter. If they're pulled in tighter, they are closer to the nucleus, and therefore their size is shrinking of the atom. Now, why are they pulled in tighter? Well, we're adding more protons. And then more protons to the nucleus means we're increasing the nuclear charge, or the force of attraction. And therefore, the electrons in the valence shell, which are all in the same energy level, they're not any further away, they get pulled in tighter. Okay, so what about down a group for the atomic radius? Well, the atomic radius increases as we go down a group. And why is that? Well, remember the force of attraction again. Let's talk about the force of attraction. The force of attraction will decrease as the radius of the atom increases. So why is the radius of the atom increasing? Well, let's just put a little nucleus here, plus. That's going to represent our positive nucleus, right? And every time we go down a group, we add another energy level. So the first energy level would be 1, and then we have 2 rings, 3 rings, 4 rings, 5, 6, and 7. And every time we add a new ring, the valence electrons in that ring get further and further away, right? Valence electrons are in what energy level? Well, they're in the energy level of what period we're in. And as we go down, aren't we increasing the number of periods? Here's period 1, which means we have 1 energy level. Period 2, 2 energy levels. Period 3, 3 energy levels, and 4. And this is the energy level that the valence electrons are in. So every time we add a new energy level, this valence electron keeps moving further and further away from the nucleus. And as it moves further and further away, the force of attraction on it decreases, and therefore the radius on it increases. So think of it like adding another layer to an onion. An onion has a bunch of layers, right? Each onion rings, and then each time you add a ring, the onion gets a little bigger. Same thing with a tree. If you cut a tree and you count the number of rings, the larger trees have more rings. The smaller trees have less rings. Okay, so let's talk about ionization energy across a period. So what is ionization energy? Okay, so ionization energy is the energy to permanently remove a valence electron. So when we remove a valence electron, we create the ion, okay? So where is it going to be harder to remove valence electrons? Well, where the energy, or where the force of attraction on them is very high. So where is the highest force of attraction on an element for the ionization energy? And that would be the element of helium, right? So let's circle that. So helium has the highest ionization energy. Why? Those two valence electrons are very close to the nucleus. They're held in very tightly. Remember the expression high, right, tight. Those electrons are held on tightly. So it's going to take a lot of energy to remove them, to permanently remove them, right? And then so your next ones are fluorine and neon, and then it just keeps going out from there, right? So the ionization energy, as we go across a period and we get closer to the inert gases, increases. Now the ionization energy decreases as we go down a group. And why is that? It's all based on the force of attraction again. As the force of attraction weakens as we go down a group, then it's easier to remove a valence electron. So the low left loose one that I wrote a couple of slides ago means that the easiest electrons to remove are those on the elements of cesium, barium, these ones right here, right? And that's not to say that the ionization energy on lithium is hard. It's just that as we go down a group, the easier ones are on the lower left, right? So as we get further and further away from basically helium, fluorine, and neon, the further away we get, the easier it is to remove valence electrons, right? So if I was to number them from 1 to 4 of the regions, this is, and then hardest is 1. Hardest equals 1. This is region 1. This would be region 2. This would be region 3. And of course, this is region 4. So 1 to 4, hard, very easy, right? Again, because it's basically how close we are to helium and neon. It's very close here, somewhat close here, further away from here, and very far away from here. So as we go down a group, the elements on the top of the group are harder to remove electrons from than the elements in that same group on the bottom, right? That doesn't mean that the elements are hard on the top. It just means that in a relative scale, they are harder than the ones on the bottom. Electronegativity follows the same trend as ionization energy. What is electronegativity? All right, there's the definition. Electronegativity is the desire of an atom to acquire electrons during bonding. Now, I'm going to draw real quick the staircase in again. And remember, the staircase separates the metals from the nonmetals, right? So the metals want to lose their electrons during bonding, and nonmetals want to gain electrons during bonding. So if you are a metal, you do not want electrons during bonding. You want to give them away, so your electronegativity value is low. If you are a nonmetal, you do want electrons during bonding. However, not all nonmetals want electrons. Which ones don't? The inert gases. They already have a full shell, so they don't have an electronegativity value, right? So the highest one is fluorine. So fluorine has the highest electronegativity value, right? So as you get closer to fluorine across a group, across a period, your electronegativity value increases. So bottom line is basically what you're looking at here is these materials do not want electrons until you basically cross that staircase. And then all of a sudden, I want electrons to complete my valence shell. It's all about completing the valence shell. It's easier for these ones to lose electrons to get to another valence shell as opposed to gain a whole bunch of electrons to get to this valence shell. Right? Fluorine only needs one. It really wants it because then it'll look like neon, which is what it wants to do. Okay. Helium, neon, argon, krypton already have all their valence electrons. They don't need any more, so therefore they don't want any more, and therefore they don't have an electronegativity. And finally, the last trend is electronegativity decreases as we go down a group. And the reason why, again, which elements want electrons? Those with this on the right-hand side of the staircase. And here's the staircase again. Let me draw that in red. Here's the staircase again. Right? So which elements want electrons during bonding? These. Which ones don't? These. So as I go down a group, I become more metallic-like. And therefore, as I become more metallic-like, I don't want to acquire electrons. I want to get rid of my electrons. Even here, you take nitrogen, which is a nonmetal, but by the time you get down to bismuth, that's a metal. So the metallic character increases as you go down a group. The more metallic something is, the less it wants to have electrons acquired during bonding. So there are the trends. Hopefully that was helpful. And then that will be served if you were prepping for a test or looking for information on to improve on your last one.